Welcome to Complex Analysis, Lesson 23, Harmonic Functions. In this lesson, we're going to talk about harmonic functions, the relationship to analytic functions, and something called harmonic conjugates. I'll give a few examples and prove a few theorems related to the topic. An harmonic function, f, is a continuous function that has two derivatives. It maps from some subset S of the n-dimensional Euclidean space to one-dimensional Euclidean space, and it satisfies the following equation, which is known as Laplace's equation. As you can see here, it's the second derivative with respect of f with respect to each one of the n variables, representing each one of the n dimensions here. And that needs to equal 0 in order for the function f to be considered an harmonic function. And we have this shorthand notation here, which occasionally we'll use. So in our case, we're only interested in the two-dimensional case because we're talking about complex functions. And so in that case, we just have two variables here, x and y, and we have this equation here. And sometimes it's written with this alternate notation, fxx, which means the second derivative of f with respect to x, and then the same thing for the second derivative of f with respect to y. So we're going to prove a theorem on this topic relating harmonic functions to analytic functions, and I'll do that on the next slide. So we have a theorem here relating analytic functions to harmonic functions. It's fairly straightforward. If we have an analytic function, f of z, broken into its real and imaginary parts, which we call u and v, then u and v are harmonic functions. And we're talking about within a given domain D. So as we stated in a previous lesson, an analytic function is infinitely differentiable, which means that the first and second partial derivatives of u and v exist and are continuous. We also have something called Schwarz's theorem, which comes from multivariate calculus, and it says that we can switch the order that we take the partial derivative. So you see here we're doing the partial of u with respect to x and then with respect to y, and then it equals the partial of u with respect to y and then with respect to x. And we can write it this way too, just as a matter of notation. Excuse me. And then we have the Cauchy-Riemann equations, which you may have forgotten, but I've written them down here on the bottom right. So if we apply these equations to this here, we substitute in for u the partial of u with respect to x, the partial of v with respect to y. We get this, and then we substitute in the partial of u with respect to y, and we put in minus the partial of v with respect to x, and we get this here. And so if we add the right to the left side, then the equation is basically the condition for harmonic function, which implies that v is harmonic. And we can do the same thing or a similar thing to show that u is also harmonic. So if we have a function, a harmonic function, I should say, u of x, y in a domain D, another harmonic function, v of x, y, and d, is said to be its harmonic conjugate if u plus iv is an analytic function. So we have a theorem about this. Every harmonic function u in a simply connected domain D has a harmonic conjugate. Basically what we're saying is if you're given a harmonic function u, you can find your v of xy, basically the imaginary part of some analytic function. So we're going to prove that by construction. Basically, we'll construct f of z, which means we're using u of xy. So we're basically constructing the v of xy. So if such a function exists, it must satisfy the Cauchy-Riemann equations. And if you recall, when we did the Cauchy-Riemann equations several lessons back, we also stated that the derivative of the function, the analytic function, took this form here. We could also write it in terms of v, but we're going to do it this way in terms of u. And then just some notation to hopefully make things a little bit easier, but we'll see. So g of z, we'll let that equal the derivative of f. And then we write g of z equals s of xy plus I times t of xy, where s equals u of x and t equals minus u sub y, which is the partial derivatives, I should say. So next we want to show that g satisfies the Cauchy-Riemann equations and is therefore analytic. Since u is harmonic, we have that the second partial of u with respect to x is equal to the negative of the second partial of u with respect to y. And that implies that s, the partial of s with respect to x, remember s equals the partial of u with respect to x. So this is, if this is essentially that, equals the partial of t with respect to y, which is essentially this, which comes from this here. So let me just pause a second to let you absorb that. Okay, and then also the partial of s with respect to y equals the partial of u with respect to x and y, and the partial of t with respect to x equals the partial of u with respect to y and x. And again, we're using these two equations here. But from Schwarz's theorem, we know that we can change the order of the partial derivative. So we have u of xy equals u of sub yx. So that means that if we make these substitutions in here, if these two are the same, then we get s, the partial of s with respect to y equals negative the partial of t with respect to x. That's just plugging this into here. And so we have the partial of s with respect to x equals the partial of t with respect to y, and the partial of s with respect to y equals the partial of t minus the partial of t with respect to x. But these two things together are the Cauchy-Riemann equations for g. So g of z is analytic. All right, we're not done yet. We have a bit more, but so far we've found that this function g of z equals this here, which is essentially the derivative of f, is an analytic function. So let's continue on the next slide. So we left off on the last slide with showing that g of z was analytic, and we defined g as the derivative of some hypothetical function f of z, and we also came up with this expression here based on the Cauchy-Riemann equations. So continuing with the proof, since D is a simply connected domain, we have by theorem 129, which we proved or stated in a previous lesson, that G has an antiderivative in D. Since G is analytic, it follows the condition of this theorem. And that allows us to define f of z in terms of a contour integral with g of z as the integrand, going from z sub 0 to z plus u evaluated at x0, y0. We'll see why this is needed towards the end of the proof. It's not obvious at this point. By the deformation invariance theorem, the above integral has the same value along any contour from z0 to z within domain D. And further, since the antiderivative of an analytic complex function, g in this case, is also analytic, we have that f is analytic. So what we need to prove is that our small u, lowercase u, is in fact the real part of f is defined here. So what we do is we let f equal capital U plus I capital V, and we want to show that our small u is in fact equal to our capital U. So taking the derivative of f is defined here, using the Cauchy-Riemann theory, we see that derivative of f of z is the partial of capital U minus I times the partial of capital U with respect to y. And then we equate these two here. And from that we get that the partial of capital U with respect to x must equal the partial of small u with respect to x. And that implies that capital U and small u differ by at most a constant, since their partial derivatives with respect to x are equal. And then if we use our definition of the antiderivative of g of z, basically this here, plug in f of z sub 0, and you notice if we go from z to z sub 0, this is 0, and then we just get u of x sub 0, y sub 0. And if we plug in z sub 0 into this, we get capital U of x sub 0, y sub 0 plus I v times x sub 0, y sub 0. Then we can equate the real parts on both sides of this equality. So small u evaluated at x sub 0, y sub 0 equals capital U evaluated at the same point. And v of x sub 0, y sub 0 must equal 0, since there's no imaginary part here. So since capital U and small u differ by at most a constant, and they have the same value at one point, that means they must be the same. And so we now have established that our u, our small u, is the real part of an analytic function. And that implies that our v is our harmonic. So we've proven our theorem. So let's do an example. We're given a function ux of y equals e to the x cosine y. We want to find the harmonic conjugate of u. So first we verify that u is harmonic. We take the second partial derivative of u with respect to x. We get e to the x cosine y, and then we take the second partial of u with respect to y, and we get minus e to the x cosine y. So in fact, when we add these together, we get 0, which means that u is an harmonic function. So if v is its harmonic conjugate, then it must satisfy the Cauchy-Riemann equations. So we have these here, and if we take the partial of u with respect to x, we get e to the x cosine y. So v, the partial of v with respect to y is e to the x cosine y, and we can do the same thing for the second Cauchy-Riemann equation. Then we can use either one of these to find y. Let's use the first one. We'll take the antiderivative of this equation with respect to y. We get v equals e to the x sine y plus a constant. We can double check that this is our v that we're looking for. We can double check that v is harmonic. So we take second partial derivatives of v with respect to x and y. We get this and this, and they add to 0, so that verifies that v is harmonic. And finally, we can say that f of z equals e to the x cosine y plus I e to the x sine y plus our constant c. is an analytic function that has u as its real part, and then our v is its imaginary part. And we can actually simplify this. This is actually e to the z plus I times a constant. So it's a collection of solutions, one for each possible complex value. So we have a few exercises to try. Given u equals x cubed minus 2xy squared, first we'll show u is harmonic, and then find its harmonic conjugate. And the hint is that u is the real part of z cubed. Same problem or same task, but different function here for our second exercise. U of x, if u of x equals e to the x squared minus y squared times the cosine of 2xy, show its harmonic, which is kind of messy, and then also find its harmonic conjugate. And again, a hint here is that this is the real part of e to the z squared. So let me explain the graph I have here. There's something called level curves. So if we take a harmonic function here, let me get the pointer. So if we have this harmonic function, f of z equals u plus iv, then if we set the real part to a constant, which I've written out here, u of xy equals a, and the imaginary part set to a constant, doesn't have to be the same one, then you get a series of curves. And what I've shown here on the right is I'm just working with the real part. We can also do it for the imaginary part, but I'm just working with the real part. So I've taken an example here, z squared equals x, which is expanded out as x squared minus y squared minus I times 2xy. And so I'm just taking the real part here, x squared minus y squared, and then setting it to different constants, 1, 2, and 3. So 1 will give you the green hyperbola, 2 gives you the blue hyperbola, and when you set a equals to 3, you get the red hyperbola. So you get an infinite number of these what are called level curves. I'll explain this on the next slide here, and I'll maybe just put a few words to it here. It turns out when you take at a given point on one of these level curves, what's called the gradient is actually perpendicular to the tangent line at that point. And I'll explain that on the next slide. Unfortunately, it was kind of hard to fit the explanation in this figure on the same slide. So I would suggest that you do a screen capture of this slide so you can look at this when I go to the next page and I explain what this particular thing means here. Okay, so I changed my mind. I decided this slide would be very hard to follow if I didn't reproduce the figure from the previous slide. I really want to just focus on this one issue here concerning the gradient. But let me first review. From vector calculus, a gradient of a scalar valued differentiable function, which we'll call u of xy, is a vector valued function using this notation here, where the vector is two components, the partial of u with respect to x and the partial of u with respect to y. And this gradient gives the direction and the rate of fastest increase at some point z. And also from vector calculus, we know that the gradient is orthogonal to the level curve at a given point. So at this point A, if you take the tangent at A, the gradient is this vector AB, and it's orthogonal to the tangent line there. So for our example, If you recall, u of x was x squared minus y squared, and we'll take the level curve when x squared minus y squared equals 1. So it's this green curve here, this here and here, but we're only looking at the right branch. So the gradient is given by these partials, so it's 2x minus 2y, since we're just working with x squared minus y squared equals 1, is our function u. And so at the point a equals square root of 2I, which is here, and we plug in the square root of 2 for x and 1 for our y into our gradient formula, and we get 2 times the square root of 2 minus 2. So that's our gradient, and that's actually a vector from 0 to 2 times the square root of 2 minus 2. So it's going this way. It's down here. Let me just draw it in roughly. So it basically looks like that. It's kind of roughly, that's our gradient. So what we want to do is move it to here, and that's what I've done. So this vector AB is this vector, and we just moved it so its tail, its initial point, is A, and then its arrow, its end point, is B. So we just moved it up to here. That's what I've done. And then my claim is that this is the vector AB is orthogonal to the tangent. And we just need to show that the slope of AB is minus 1 over the slope of the tangent line. So the slope of AB is minus 1 over the square root of 2. That's just the change in y over the change in x. So it's minus 1 over the square root of 2. And then if we go about taking the derivative of x squared minus y squared equals 1, we find that it's y over x. And so its slope at this point A is the square root of 2 over 1. And so you can see that the two slopes are the negative reciprocal of each other, which is, as we know from basic algebra, that means the two lines, or the two vectors, are orthogonal. So turns out that's true in general, and we'll show that in the following slides. So what we have here on the right is an enhancement, or an addition to the figure we had in the last two slides. We again have the level curves for u of x, y at 1, 2, and 3, but we've added now the level curves for the imaginary part of f of z equals z squared at 1, 2, and 3, and we get these curves that I'm pointing to here. It turns out that the level curves for the real and imaginary part of a analytic function intersect at right angles. And that's true in general. It's not just true for this example. You can kind of see it looks like it may be true here if you draw the tangent line at B for the red and for the green curve. They kind of look like they would be orthogonal, but in fact we can prove that. So before we prove our theorem concerning the level curves intersecting at right angles, we need to refresh our memory of something called the dot product, which is what I have here on this slide. So if we take two vectors, you can think of them as being complex numbers. The dot product is just the x times s and y plus y times t. And that's equivalent to the norm of A times the norm of B times the cosine of the angle between A and B, where the norm is just the same thing as the modulus. And the point we need, or the idea that we need here, is when the dot product is equal to 0 and neither A nor B are equal to 0, then the two vectors are orthogonal or perpendicular. And that's because when this equals 0, the cosine must equal 0, and that's when theta equals 90 degrees, or pi over 2. So we'll use that in the proof on the next slide. So let's now prove the theorem I mentioned a few slides back. The level curves associated with harmonic conjugates intersect at right angles. So basically, the level curves of the real and imaginary part of an analytic function intersect at right angles always. So we let U and V be harmonic conjugates. Then the definition of the gradient, just writing it out here. Then we take the dot product, as we talked about on the previous slide. So we get this expression here. And then the key part is we have the Cauchy-Riemann equations, and we can make some substitutions here. U of the partial of U with respect to x equals the partial of V with respect to y, and the partial of U with respect to y equals negative the partial of V with respect to x, and we get the same term here and here, so they equal 0. And from what we said on the previous slide about dot product, that means that when the gradients are not 0, they are orthogonal, and that means that the level curves are orthogonal at points of intersection. Okay, so that's the end of our lesson. There's a lot more to be said about harmonic conjugates. This is just a short overview. If you look at two of the references I gave, the book by Saff and Snyder and the other one by Brown and Churchill, they both go into more detail, and they also give some examples. There's a lot of applications of harmonic functions to physics, which would take me into several more lectures, but I'll just refer you to those two books for more information and examples based on applications to physics.